Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we are going to talk about disaccharides. And so disaccharides are carbohydrates that's composed of two monosaccharides. And these monosaccharides are going to be covalently bonded or linked together covalently. And this covalent bond is known as a glycosidic bond. And so whenever you have monomers of a specific macromolecule, in this case, the macromolecule is a carbohydrate, the name of the bond that links the monomers together, it's going to be termed very specifically. And so, for example, for amino acids, that's going to be a peptide bond, where for carbohydrates, it's known as a glycosidic bond. And so this glycosidic bond was created through a dehydration reaction that's typically catalyzed in an organism by an enzyme. And so we'll take a look at the formation of a glycosidic bond a little bit later. For now, just be aware that the glycosidic bond is is found within that structure that I'm circling in blue. So this is a glycosidic bond, this is a glycosidic bond, this is a glycosidic bond. And so the three most common disaccharides that we're going to look at is going to be sucrose, lactose, and maltose. And so the first disaccharide that I want to discuss is lactose. So lactose, it's a disaccharide that's found in milk and milk products, and it contains two specific sugar subunit, which is galactose and glucose. And so I'm just going to go ahead and scroll up again. And I'm just going to circle that this is lactose. So this is going to be galactose and this is going to be glucose. And notice that they're covalently bonded through a glycosidic bond. And so galactose and glucose, when formed together, they make lactose, and lactose makes up about 6 to 8% of human milk, 4 to 5% of cow's milk. And so typically, these carbohydrates are used as fuel in the form of ATP. And so they have to be broken down. The enzyme lactase is going to catalyze the reaction of separating or destroying, if you will, this glycosidic bond so that the glucose subunit can separate from the galactose subunit. And so once those sugar monomers are separated, then they can go into whatever chemical pathway that's prescribed for them to either function in specific cell structure, or it can be used to harvest energy. Now, individuals who do not have or no longer produce the enzyme lactase, they will become lactose intolerant. And so if they were to ingest these milk-based products, the typical symptoms that they would experience is abdominal cramps and diarrhea. And so for those who are lactose intolerant and still want to, digest or eat some cheese, have some ice cream, and the list kind of continues, or the cheese on the pizza, then they can go to the drugstore and, pick up a pill that contains lactase. And so you ingest this pill, the outside of the pill will dissolve in your stomach, releasing lactase. And so when you eat your food, the lactase inside your stomach is going to start breaking down the lactose into its monomeric form, which is galactose and glucose. Maltose is another disaccharide, and it's known as malt sugar. And so this is the structure of maltose, and maltose is composed of two glucose units that's covalently bonded together, once again through that glycosidic bond. And so maltose is composed of two glucose molecules, and it's commonly obtained from hydrolyzing starch. So any starch-based food or starch-based products, if you hydrolyze it, and starch is a polysaccharide, by the way. And so at some moment in time, you're going to get like these disaccharides that is going to be maltose. And so if the disaccharide maltose is digested or hydrolyzed even more, then you'll get two glucose molecules. And so maltose is typically used in cereals, candies, and in brewing. If you recall from the very first lecture video for this chapter, maltose is not as sweet as, for example, sucrose. And so this image right here, I thought it was interesting. And so it just lists the top 10 foods that have the highest content of maltose. And so apparently pancakes is number one. I'm sure the reason why pancakes has a high content of maltose is one, it's processed. Number two, it actually is dependent on the type of flour that you use. So just because you make pancakes doesn't mean that you have a whole bunch of like maltose. You have to also consider the type of flour or the flour that you guys use. Sweet potatoes is comes in second, and so here we have about 11 grams of maltose versus 11.5 grams of maltose. And so when you guys are looking at this fried onion rings, it's referring to the batter, not the actual onion. All right, so sucrose, which is the third common disaccharide, is also known as table sugar. And so sucrose is primarily found in sugarcane and sugar beets. And so sugarcane, so this is an image of a sugarcane. It's typically processed in some type of plant. And so the sugar that we typically buy has been processed in some form. But what's really cool is that if you guys ever have the opportunity to travel into like some type of Asian country, typically there might be stalls that you'll see that they'll sell, sugarcane. And so you guys can purchase that sugarcane and just start biting right into it. Just kind of like suck out all of the sucrose that's inside that sugarcane. There's also stalls where they take raw sugarcane and then they put it in this machine that kind of like squeezes out all of the juice, and you guys can just drink the sugarcane juice, which is it's actually not very sweet, but it is nice and sweet. I like it. So for those who like to bake, they can also use beets as a substitute for processed sugar. So with beets, you guys just have to be very careful. So for example, if you want to use beets to make red velvet cake, you can, but you would have to add something acidic like lemon juice or tartaric acid or buttermilk to ensure that the color stays red. If you guys don't acidify your cake batter when making red velvet cake, the chemical component that would produce that red color is easily oxidized. And so when you guys bake it, and if you don't acidify your batter, your cake is going to turn brown. Not that it's like bad or anything, but you just can't say that it's red velvet. And And so looking at the structure of sucrose or table sugar, here we have a glucose molecule, and here we have a fructose molecule. And so once a glycosidic bond is formed between them, you guys have this disaccharide called sucrose. Okay. And so let's go ahead and talk about glycosidic bonds a little bit more. And so these glycosidic bonds allow two monomers to be covalently linked to each other. And covalent bonds are pretty strong bonds, so it's really hard to separate those two apart without some type of catalyst. And so the functional group that's found in a glycosidic bond are typically ethers. So remember, ethers have this like COC feature to them. And so in terms of the formation of the glycosidic bond, here we have the anomeric carbon for glucose. And this is going to be the anomeric carbon for fructose. The reason why this is the anomeric carbon for fructose is because of the numbering system that they've labeled. So this is 1, 2, 3, 4, 5, 6. In the previous lecture video, when I was showing you guys how to draw those Haworth structures, we went clockwise. So they basically took fructose, they drew it normally, and then they just flipped it so that both of the anomeric carbons between glucose and fructose are facing each other. And so anyways, the hydroxyl group that's on the glucose and the hydrogen from the hydroxyl group that's on the fructose, they're going to come together. And so if you have OH and H, you get water. And so the formation of a glycosidic bond was through a mechanism known as a dehydration reaction. Okay. Now, if you guys are going backwards, if you guys are going from a glycosidic bond to the monomers, so if you guys want to destroy the glycosidic bond, then the process is known as hydrolysis. So lysis is to like break or burst or whatnot. Hydro, water. Okay, so you're using water to lyse or to break or to separate this glycosidic bond. Where dehydration, so dehydrate, you have loss of water. So here you're taking water out. While for hydrolysis, you're adding water in. And so the dehydration reaction will, between two monomers, will form your glycosidic bond. Adding water into the glycosidic bond will result into the separation of your disaccharide into two monosaccharides. So that's known as hydrolysis. And so in terms of the numbering of glycosidic bonds, so the glycosidic bond can be determined by the number that the alcohols originate from in their monosaccharide form. And so if you are trying to describe the numbering system for this glycosidic bond, here we have the combination of 1 and 2, right? And so I think we're going to go through some examples that doesn't involve sucrose. So I don't want to write any answers just yet because we need to really understand the numbering system before we talk about the numbering system for sucrose. All right, so let's just say that we have galactose and glucose. So by the way, if you have galactose and glucose, what disaccharide is this? And so if you had said lactose, then you're absolutely correct. And so remember that lactose is galactose and glucose. Maltose, that's two glucoses together. And sucrose is glucose and fructose. And so looking at the formation of this glycosidic bond, it turns out that it is the beta form of galactose that's going to, so the hydroxyl group of the beta form of the galactose is going to pair up with one of the hydrogens. And so notice that the numbering here is carbon number 4. And so unlike the previous example, the formation of the covalent bond or the glycosidic bond for galactose and glucose does not involve both anomeric carbons. And so there's a significance to that in terms of their chemical properties. And well, we'll talk about that when we get there. And so one way to name this glycosidic bond is to discuss the origin, the carbon number of where that hydroxyl came from and where that hydrogen came from to form water. And so notice that this carbon 1, came from the beta form of galactose, where the hydrogen, this hydrogen right here, is coming from the 4th carbon. So we would name this glycosidic bond beta 1,4, beta dash comma 4 dash glycosidic bond. Okay. And so if you guys are looking at this example, here we have glucose and glucose. Remember, if you guys have two glucose units together, covalently bonded together, then what you guys have is maltose. Once again, since this hydroxyl group is originating from carbon number 1, and this hydrogen is originating from carbon number 4, then we would go ahead and describe this glycosidic bond that they form after a dehydration reaction has occurred as alpha 1,4 glycosidic bond. And so 1 and 4, hopefully you guys understand where those numbers came from. Why is it alpha? How come it's not beta? And so it's this alpha is describing the position of the hydroxyl group on the anomeric carbon. And so if you guys recall from the previous lecture video when we were talking about Haworth structures, the alpha represents a hydroxyl that's pointing below, or it's down below the ring. And so since carbon 4 is not an anomeric carbon, we do not use alpha or beta to describe it. We just simply say the hydrogen is coming from carbon number 4. Okay. But since this hydroxyl group is coming from an anomeric carbon, we have to communicate to the reader the stereochemistry of that specific carbon. So that's why it's called alpha 1,4. And so typically that alpha pertains to the first number that you guys see. And that first number that you guys see is the carbohydrate that's going to be on the left-hand side. Okay. All right, so let's go ahead and talk about glycosidic bonds again with respect to sucrose. And so earlier I mentioned that for sucrose, both anomeric carbons are contributing to form that glycosidic bond. And so here we have an alpha, and in this case, since this anomeric carbon is carbon number 1, we're just going to say alpha dash 1. Now for the fructose, notice how the OH is popping up. And so since in fructose the hydroxyl group is above the plane of the cyclic ring, then we're going to have to say that it is beta. And so since it is on carbon number 2, we're going to have to say, beta 2. Okay. And so we're going to go ahead and combine both of these together and describe the glycosidic bond as a alpha beta 1,2 glycosidic bond, where the alpha is going to represent the first number and the beta is going to represent that second number. And so that would be the name of the glycosidic bond. And once again, notice that OH and the combination of H, as you guys see here in pink, will form water. And so this is a dehydration reaction. Okay. Notice that water is no longer part of that chemical structure. Okay. All right, and so here I did pose a question, why is there no alpha or beta before sucrose? It shouldn't be before, it should be after sucrose has been made. So if you guys look at the structure, the anomeric carbon is right here and right here. And so for sucrose, both anomeric carbons are involved in the creation of this glycosidic bond. And so at the very end, there are no free anomeric carbons. Okay. Now, if you guys are looking at maltose and lactose, so I'll just go ahead and scroll up here. Notice that only one of the carbons is anomeric, but the other carbon is not anomeric. So this is the anomeric carbon, and the other carbon is not anomeric, meaning that the anomeric carbon of the second sugar molecule, this guy, is free to undergo another reaction. Okay. Now, if you guys are looking at the lactose, once again, you'll notice that the anomeric carbon on the molecule on the left is being used to form this glycosidic bond, whereas the molecule on the right of that glycosidic bond, it's carbon number 4 that's participating, and carbon number 4 is not the anomeric carbon. And so this is the anomeric carbon, for the second molecule in this disaccharide. And so since this anomeric carbon is free, so to speak, it's a free anomeric carbon, this anomeric carbon can undergo another reaction. And so in terms of the chemistry of these, carbohydrates, if your anomeric carbon is not participating in the double bond or in the glycosidic bond, then it can create another glycosidic bond with another sugar molecule. Instead of a disaccharide, you get a trisaccharide. And if the anomeric carbon of the third sugar molecule is quote unquote free, then it can react with a fourth sugar molecule to create an even longer chain of a sugar molecule. And so if you kind of like think about this as a domino effect, if the carbohydrate that you are attaching onto this long chain has a free anomeric carbon, it can continue adding more subunits to it. And that's how you would get like a polysaccharide. And so, unfortunately, for sucrose, since both anomeric carbons are being used to form the glycosidic bond, then the sucrose can never form a chain of a sugar molecule. So it can only stay as a disaccharide, right? And so both of these anomeric carbons are being used to form only one glycosidic bond. And so none of the other carbons have the chemistry, the right chemistry, so to speak, to react with another sugar molecule. Okay. And so this is important because we can go ahead and test this idea of having a free anomeric carbon or not having a free anomeric carbon. And so this is known as Benedict's test. And so we can go ahead and use Benedict's test to confirm the presence of reducing sugars. And so there's a lot of things that I need to discuss here before we talk about this actual chemical reaction. So let's go ahead and focus on this terminology, since that's pretty new. What is a reducing sugar? And so, in short, a reducing sugar has an anomeric carbon that is free so that it can undergo a reaction with something else. Okay? And so the idea is that if you have at least one free anomeric carbon, then this whole sugar, no matter how long the chain is going to be classified as a reducing sugar. And so the word reducing sugar comes from the reaction, from this Benedict's test. And so the Benedict's test involves an oxidation reaction with this copper 2 ion. And so if you have a reducing sugar, then the functional group, whether it's an aldehyde or a ketone, is going to be free, quote unquote, to react with this copper ion. And so when this oxidation reaction occurs, this aldehyde is going to reduce copper. And so remember, reduction means gain of electrons. And so this copper is going to gain electrons from this aldehyde and thus becomes reduced. Right? So that's where the word reducing sugar comes from. This sugar has the ability to reduce another substance. And in turn, itself becomes oxidized. Okay. And so for Benedict's test, if your solution stays blue, then that means that there was no reducing sugar present. However, if your Benedict's test goes from blue to brick red, then that means that there is present in your solution a reducing sugar, because this aldehyde somehow gives this copper 2 electrons to form this brick red substance. Okay. And so we have typically the Benedict's solution has a range of colors. So if the solution is blue, then there's no reducing sugar. That means either one, you have a carbohydrate in which there are no free anomeric carbons, or two, you might not have a carbohydrate in your solution to begin with. Now, if your Benedict solution turns green, you'll have some traces of reducing sugar. Orange, moderate amount. Brick red means that you have a lot of reducing sugars. And so we can go ahead and use the Benedict's test to actually identify if we have a carbohydrate with a free anomeric carbon on its tail end, or we might have a carbohydrate that is non-reducing, meaning both of the anomeric carbons have somehow been used to form that glycosidic bond so that no other reactions can occur. And so the mechanism of this reaction is, well, I'm not going to show you the entire mechanism, but if you guys recall, the cyclic compound is the most thermodynamically stable conformation for a carbohydrate. And so this is your hemiacetal, this is your anomeric carbon. So at some moment in time, even though this is the ring form is thermodynamically stable, your sugars can revert back to its linear form, to its open form, if you will. And when that sugar opens up, it reforms this aldehyde. And so the presence of the aldehyde allows it to interact with copper 2 plus for the Benedict solution, reducing the copper 2 plus, and it itself becomes oxidized. And so the same similar mechanism can occur for ketones. And so here we have fructose. Fructose is a ketose. So once the ring kind of opens up, the ketone is kind of available. And so let me see here. So I think there's a slide. Did I pass it? I guess I passed it. Anyways, so the idea is that this ketone will actually conform and produce an aldehyde. And then the result of that aldehyde is what's going to react with Benedict's reagent, which is copper 2 plus, producing that brick red color. And so when you guys are studying this, the main point is what is a reducing sugar, right? And so very loosely, a reducing sugar implies that there is a free anomeric carbon that's on the tail end of a carbohydrate chain. Okay? And when that anomeric carbon is still available, in other words, it hasn't undergone some type of reaction, it can reduce the copper 2 plus for Benedict's reagent, producing a different colored solution that would signal to us as scientists that there is present in solution a carbohydrate that has a free anomeric carbon somewhere on its end. Now, if your solution stays blue, then that means that your sugary solution, if you will not be able to reduce the copper 2 plus. And since it cannot reduce the copper 2 plus, copper 2 plus will just stay blue. Okay. And so overall, lactose and maltose are reducing sugars. The reason why is because they have that anomeric carbon at their tail end that's free to undergo another reaction. Same thing here. And so at some point in time, this cyclic ring is going to open up. And when it opens up, it's going to produce this aldehyde. And this aldehyde is what's going to reduce the copper 2 plus. And itself becomes a carboxylic acid. Okay. Now, once again, sucrose are non-reducing sugars. Once again, the reason why is because both of their anomeric carbons are participating in the formation of this glycosidic bond. And so if both of their anomeric carbons were used to form this glycosidic bond, then it itself cannot undergo any other reaction. So it's kind of like a dead end. Okay. And so I talked about hydrolysis earlier. Hydrolysis is just the addition of this water molecule to break up this glycosidic bond to reform the OH, the alcohol, or the hydroxyl group that's present in both of those sugar molecules.